Okay, so I'm going to have a nice weekend because I don't have a quiz coming up. But I thought it might be nice to show you what I skipped in the lecture yesterday. And through the magic of OneNote, there is absolutely no error anywhere. So what I forgot to do yesterday, which I should have remembered right away, and I was asked about this during the lecture, is why did we calculate the relative accelerations of A and B? And so, again, if you look at this diagram right here, you have a bunch of constant lengths, but the only ones that vary are XA and XB relative to A. And you can use that to calculate the total length of the cable. Taking its derivative, you then get a relationship between acceleration of A and acceleration of B relative to A. This is, of course, not zero in the sense that there is an acceleration of B, but it is zero as far as the length of the cable is concerned. So it's two separate problems that you're dealing with. And when you do that, you end up with this relationship, acceleration of A equals negative, twice acceleration B with respect to A is equal to negative 2B with respect to A. So again, remember, one of the things with cables and cable lengths is that you always have the rate of change of length. So now, sort of translating that into this, you have the acceleration of B, which is equal to acceleration of A plus the acceleration of B relative to A, and you can substitute in immediately this minus 2A. And intuitively, this actually makes sense. So now I have a relationship for the kinematics between acceleration of B with respect, or B and A. So how does that change things? It doesn't change anything actually, except down here. So in this relationship, you have a tension that is at first dependent on acceleration of A, of course, and then you substitute in and you substitute all the relationships you've already calculated. And you'll get this relationship in terms of AB. Once you do the substitution, and if everything works out, by the way, tonight, tomorrow morning, around 11 at the latest, you will have the entire set of notes for particle kinetics. So second law. So all of these notes should be online. I probably will not announce them because I find that the announcements are getting a bit overwhelming. So I'm just keeping the supplemental videos as a weekly thing. I've deleted all of the quiz announcements. And the reason I did that is that you don't need to see a quiz announcement for something we've already passed. Okay. Questions? Go ahead.
In the sum of the x forces, shouldn't the sum of x forces then equal negative MAA? Because now we're putting the
Yeah, so what will happen is you got T on the right-hand side, you brought minus MAA, and then you substituted negative AB.
So you got positive now.
Yeah. So this is not a problem to visualize. Don't look at this problem as a problem that, hey, he did it in lecture, it's pretty straightforward. Try to do this one on your own. And the reason why is that next week, I'm actually going to do another problem very much like this. And the reason I'm going to do it is I'm going to look at work. And the reason why work becomes interesting is not the acceleration terms, but the velocity term right here, because work is related to force times distance. And the distance of B is twice the distance of A. And so you're going to find out that you actually have a system with internal work done because of this. But that's sort of going 2 lectures ahead. But it's a good example. This is a really nice example for you to try on your own.
I'm a bit confused for the first part. Why do we have like one equation saying 2AA plus AB equals 0 and then
Okay, so these are two separate equations, and I probably have not explained that well. So the one in green deals with the chord length. This one is the box displacements. So even though those two things seem to be saying two separate things, one is talking about the chord and the rate of change of the length of the chord. So for example, the simplest one is really to go with velocity, and the rate of change of A is going to be twice as much as the rate of change of B with respect to A. So, or it's going to be half actually. But when you do relative velocities between two objects, one sitting on top of another, you have the velocity of the bottom object and the velocity of the top object. And so when you have a look at the top object, it's the velocity of the top object relative to the bottom. And that's why I end up now with two seemingly contradictory equations, because these don't make sense, because otherwise AB equals 0 or some form of 0, minus plus AB and all sorts of things. That's not what it is. Okay. So if you can separate out both of those, then you can solve for the kinematics. And it's important to be able to do this. Go ahead.
Is there some rule for how you come up with combinations for x and b, because how do you come up with x being
So,
x b?
yeah, so that's also, so the question is a common one, and it's really kind of tricky. So if you look at this problem the first time you do it, and I can almost guarantee you about 70, 80% of you will look at this problem, even though we've done it in lecture and I've written it this way, you'll write xb on the top. And the reason why you do it is because intuitively that makes more sense. But you have to remember, B is not moving relative to the floor. B is moving relative to A. And so this is a major step in terms of understanding this motion. So one of the reasons why I kind of recommend doing problems like this on your own is that, one, you will find yourself sort of saying, well, why did he do this at that point? And it's helpful that you look at a couple relative velocity questions and absolute dependent motion, by the way, just to understand how these sorts of things work. But the important thing is, two objects, one on top of each other, the one on top is going to have a relative motion. All right. So I will put this actually, so this is going to end up being kind of a mess this week, because I'm going to put into OneNote two copies of the same example. So there you go. But I was doing this one, and I just have to find my lectures. Oh, there. And so if you remember, this is, again, a problem that looks very complex. And there are a lot of really complex kinds of motions that you're dealing with. You have a small ball at rest at the top of a frictionless semicircular dish surface. The ball is given a slight nudge, so it slides along the surface. What is the angle theta at which the ball separates from the surface? And what you're looking for is when the normal goes to 0. And you will deal with problems like that next week when you do work energy homework. And in fact, there's a roller coaster problem that'll drive everybody crazy, and I'll end up spending a lot of time on Piazza because of it. But you're kind of looking at what the motion is and what the normals are. So the first thing is to sort of realize that you're given r and theta here, so it's really a nice r-theta problem. And two is not to overcomplicate. Well, maybe we'll leave that there. Is to remember what your equations are. And again, this is really good practice as you're studying this for this course. And there's lots of stuff that we expect you to know. one of the things we expect you to know is these equations for AR and A theta. Simplifications occur from that. But you have the free body diagram, you have the accelerations, and from these accelerations, I can write my standard sort of equations of motion. I have sum of forces in R, I have sum of forces in theta. Sum of forces in R is n minus mg cos theta, MAR. Sum of forces in theta, mg sine theta, MA theta. And again, very complex looking motion, but once you draw the free body diagram and look at what's happening, there's only two forces, weight and the normal. So as the weight and normal are there, you kind of go on and you sort of say, okay, I've got relationships for A theta, and theta double dot is d theta dt, and I can write an equivalent equation that we will use a lot more in chapter 5, but we'll start to use here for acceleration, which is v dv dx. So that equation becomes theta dot v d theta dot v d theta, which is s. So it's the same sort of relationship. It's going to end up with the same units, rads per second squared. But remember, rads aren't really units. So they don't, if you have multiple rads, you don't sort of square them. So your equations then become n minus mg cos theta minus equals minus mr theta dot squared, g sine theta equals r theta double dot. And if you go from that, you can write n, why are you doing this to me? N, oh. You can write theta dot d theta equals g over r sine theta d theta. So I'm just substituting into this, splitting it up, and integrating correctly on theta dot, actually, and 0 to theta. So my limits on the integral are unknown, but I have theta dot, I have theta. I have an integral on theta dot, g over r sine theta, do the integral, and I end up with theta dot squared equals to 2g over r. I brought the 2 over to this side, 1 minus cos theta. And remember, that's from the integral limits. Okay. On the other side, I have n minus mg cos theta equals mr negative theta dot squared. Okay, so theta dot squared I already know. Tunk. So I have now a relationship between normal force and the weight. And you'll notice also that I haven't really defined the weight. Or did I? I don't think I did. I don't need to. But yeah, I haven't told you anything at all about anything, really. This is still sort of an idealized problem in the sense that there's no mass associated with this that I know. I don't know what the radius is, but I just know what the normal force is. And so if I calculate the normal force, it ends up being n equals mg 3 cos theta minus 2, or cos theta equals 2/3, or theta equals 48.2 degrees. I like one note, but it drives me crazy. There we go. So theta dot, or theta at which the separation occurs. Now you look at this problem again, and you realize that you don't know very much in terms of any of the physical parameters. I haven't talked about r. I know what g is because we're on Earth. M cancels out, disappears. And so the important thing to realize is that you set n equal to 0. And this is, at that point, this thing will just fall off. And you'll deal with a lot of problems where the normal force goes to 0, and when the normal force goes to 0, everything sort of disappears. A couple of things I want to talk about first.
Could you zoom out for a second, please?
I'm sorry?
Could you zoom out?
Yep. And again, if everything works out tomorrow, by 11 o'clock for sure, it will be up. It'll be in the module for my notes. All right. So got that, got that, got that. All right. Let me just zoom that all the way up. Any questions on this? The other, just really quick if you don't mind. I just realized I should say it. The other thing to realize is that, oh good, I have a wind tunnel motor controller and it wasn't working and it just started to work again. The other thing to realize is that this problem is easy in terms of the math. The hard part really is this. That is something that you have to do a lot of to convince yourself you're not missing anything in the course. Okay. Which is very good news and saves me a lot of trouble and calling an electrician and all the rest. Sorry, you had a question in the back. So how I got that, remember that in this particular case, the integral that I did had limits of 0 to 1, or 0 to theta and 0 to theta dot. And so I end up with a 1 term. If you do the integral and solve it, then you'll get those terms. Okay, so the cos theta comes from the integral of sine theta. Sorry, I'm kind of... What? Yeah. Over here. Oh, sorry. Okay, so I substitute this in to get this relationship for r theta double dot. Oh, sorry. I use r theta double dot for what? Oh, r theta double dot to get d theta, d theta, d theta, d theta. So theta dot, d theta, d theta dot. So what I've done really simply, and it's easier to write it, equals r theta dot, d theta dot, d theta. And so from that, I can make a substitution on so I've got that. So I have it in here. Then I have theta d theta. So g sine theta equals, I really hate doing this like this, over r equals theta dot d theta, and then I split the integral, or split the derivative, differential. D theta dot is equal to that. Okay? So often when you're dealing with these problems, I want to have it in a form at the very end that ends up being theta dot d theta dot, and all the rest of the terms on this side, and that's how I'm sort of splitting it. I'm also splitting it by taking this over to that side. Okay. Standard operations at this point. You've done the same thing with dv dx. So if you had v dv dx, you know already you'd have a form very similar to this. This would be v dv. That would be 0 to v. and this would be 0 to x g over r sine of x dx. So in a linear sort of description, it's a lot easier potentially to visualize than it may be in an, a rotating environment. Okay. And that I might edit so it's a little bit cleaner on the notes. Units. So when we talk about SI units, everybody knows sort of what they are and everything's great, but it is a mass, length, and time unit. And in order to get a force, I have to multiply a mass times acceleration. So I'll end up with 1 kilogram multiplied by 1 meter per second squared. And I'll end up with those terms. On the other hand, when you deal with US customary units, English engineering units, there's a lot of sort of standard thought about this. It is an FLT system. Force, length, and time are defined. And what's problematic is that if I want something like a mass, no problem, it's 1 pound divided by 32.2 feet per second squared. Yeah, I call it a force even. And if I go to British gravitational units, I get 1 pound force divided by 1 foot per second squared, which equals 1 over 32.2 pounds force per feet second squared. Yeah, and 1 pound force per foot second squared. Okay, I get confused with slugs and pounds and pound masses and all the rest. And in particular, I will tell you I hate this system right here. Because I call two things a pound mass and a pound force. They don't have equivalents. I realize that when I deal with kilograms and newtons, I can translate those through gravitational acceleration. Was there a question? Okay. You just have to realize the difference between the two systems, and you have to be extraordinarily careful. There's a lot of argument, and has been for years among the engineering community, that one of the advantages of English engineering units is that if you want to use them, you have to be very careful. So they guarantee an improved calculation. I find that I mess things up a lot easier. SI, okay, I understand. Now, we've already done, we've already defined these. The whole chapter 3 and chapter 4 are primarily just writing these equations and setting up your axes so that everything works out. So the first one, of course, is at the top. Just all of the forces in x, all of the forces in y equals all of the accelerations in x and y, respectively. However, if you go to a normal tangential system, again, one that's targeted to the particle, you have all the forces in the normal direction. You have all of the forces in the tangential direction. Of course, they're not going to be the same between coordinate systems. The resultant force, the total force, is is equal to mass times acceleration tangential and normal. So the last one, no surprise, you're missing it. Is sum of forces in R is equal to m times AR. Sum of forces in theta equals mass times acceleration in theta. And just as a reminder, because I know this is sum of the forces in N, mass x double dot, which equals m dv dt. Sum of forces tangential, sum of forces normal equal mv squared over rho. So you're going to just have to realize that one term deals with the tangential changes of velocity, m dv dt, and the second term is dealing with change in direction. Then you come to this one, and again, this is something that really should be in your crib sheet. And at this point, I would actually start writing a crib sheet for the midterm, which I know is about a month away. But putting all of these things together now makes it a lot easier for you to choose what you want then. Again, standard definitions, and you're not going to do anything different. But your big problem is always to break it down and describe the forces in R and the forces in theta in our theta system and its corresponding accelerations. So So if you have a force P, so here I have a particle traveling along what I expect to be the path. It's defined with respect to r, or an origin as a distance r from the origin, theta out. P is pushing this particle along, and I have a particle that is traveling along that path, which is f of theta. F of theta is going to then allow me to calculate what the immediate tangent is at any one point. And I need that tangent in order to calculate the normal force. So you know that if you have a particle traveling along a straight road, you have a normal force acting up on it. What happens if you have a curved path? And how do you define that normal and that tangent? So this is what you do. So you have that. You have to sort of look at it. And the friction force is going to act along a tangent, and it's opposite to the motion. So you have friction forces that you're used to, and all of this sort of continues. So if you look in the book, you'll see sort of a very quick description of this, but this is what you're looking at. So I want to know what that tangent is, because if I know the tangent, I can then describe the normal acting on it and whatever friction forces F are acting there as well. So tan of psi is equal to r d theta divided by dr, which is equal to r over dr d theta. And you kind of look at it here. You have theta, you have a displacement d theta. The arc length, the distance displaced is r d theta over, and I kind of exaggerated that a little bit. But there you can calculate dr, there you can calculate d theta, and you have r as a function of theta, so you can do all of the rest of the things that you need to do. This is a useful equation to keep when you're looking at curved path motion. Another quick thing, as with everything else, from sort of the left-hand rule, or sorry, the right-hand rule, nobody likes left-hand, you have psi positive in the counterclockwise direction, psi negative in the clockwise direction. So again, if you put your hand at the origin, wrap your fingers around, that's the counterclockwise direction. Go ahead.
Is psi a force?
Psi is not a force. It only describes the tangent. So it is the tangent between r and the path. So if I have a curved path, if I have a circle, the tangent is just the straight line normal to that. So yeah, it's a position vector. So if, for example, I had a circle, that's there, I want to know that point right there. So that's the tangent of the curve at that instant. But
Is it like a unit vector, or does it have magnitude?
it has magnitude, but it's radians. Radians or degrees. Either one is fine. I would suggest drawing it. So take a few minutes, do a couple. I'll try. I don't know if I'll do an example today, but we'll see. Okay. On this? Okay. We always want to know what the normal direction is and what the tangential direction is of a particle in an r-theta system. We don't have to know that in an NT system because we always describe it with respect to the curved path. So it's going to be different because the origin on a NT system, well, there's no origin, but the center of curvature is just going to be straight through there. Right? So that for an NT, you point in towards the center of curvature. For an r-theta system, you got to reorient everything. And when you reorient everything, you end up with this relationship right here. So in terms of r dr d theta, where you have r as a function of theta, and theta is defined down here. You're going to spend time on this. Hold on.
So this is when the radius is moved before, like, as a function of your angle?
That's right. So I know the path, and r is equal to 6 tan theta or something of that nature. And I think you've done examples of that. Let me see if I don't do any major examples on that. Okay, let's do this one. I'll probably regret it. Cantilever cylinder, relative velocity, arm on a semi-cylinder. Okay, let's look at one that does do this. So here I have a system that consists of an arm which is pinned at point O and is open all the way through. So these light blue area is actually an open area, allowing the pin to sort of roll in there. So as it rotates about point O, that cylinder, or that pin, is going to go around the semi-cylinder. You're given an arm of theta dot equals 2 rads per second. We'll start with that. Go there. Theta double dot is 0.8 rads per second. Now, the other thing to realize is that with all of these problems, you don't care about what's happening in the next instant. You don't care what's happening in the previous instant. You just want to know what's happening at that instant. So when theta is equal to 30 degrees, find the force of arm A, OA, on the cylinder C, right there. And I'm actually going to move this over here so I can do a couple quick calculations. RC equals 0.6 cos of theta. R dot C. Oh. So this right here, ooh. Okay, so you have that arm, you have the center of the circle. The radius of that semicircle is 0.3, 3 something. It doesn't matter, 0.3 meters. And the instantaneous position is r equals 0.6 cos of theta. So r dot c, if you take its derivative, is minus 0.6 sine theta dot sine of theta, and RC double dot equals negative 0.6 theta dot squared sine theta plus theta double dot cos of theta. All right, so we have r's. Go ahead.
How did you, you took the derivative, would it be theta dot squared cosine theta?
Oh, no, it's derivative of, it's chain rule. Oh yeah, it is cosine. Yeah, and that should be sine. Thank you. So if you put all the terms in and you extract everything out from there, you have that relationship for theta dot and theta dot squared. You're given theta, which is 30 degrees, theta dot, which is equal to 2 rads per second, and theta double dot equals 0.8 rads per second squared. So RC is equal to 0.52 meters. R dot C, maybe I don't. I'm going to end up moving things around after the fact. minus 0.6 meters per second, and r double dot c is minus 2.32 meters per second squared. Theta dot 2 raised 0.8. Okay, so I have all of that. I have all I need to describe the acceleration in the radial direction, all I need to describe acceleration in theta. Acceleration of r double dot, minus r theta dot squared. Acceleration theta equals r theta double dot minus twice r dot theta dot. AR equals minus 4.4 meters per second squared. Minus 1.98 meters per second squared. So you're just substituting in numbers. The important first step is defining what r is as you move along that sort of angle. All right. So So in this case, I have the center of rotation, and I have the center of the circle. So tan of psi is equal to RC over drc d theta. RC equals, no, it doesn't matter. Psi ends up being 60 degrees. So if you start out with 30 degrees in terms of the origin, or in terms of the circle, you end up with 60 degrees for this. So it's a complex looking motion that actually ends up with a nice number. So you got 60, 30, you got all of that. You have psi here, and you have sum of forces in, oops. You have a normal force, you have a force of O on A, you have a theta, and you have a r. So you have all of the terms that you need to make this work. You have acceleration, you have the directions, you have the tans, and you end up with sum of forces in r is n cos 30, which equals 0.5 AR, force of theta, FOA, minus n sine 30, which equals 0.5 A theta. Okay. Again, getting the psi term, the tangential angle, is the important part. Drawing the diagram is kind of important. It's not as hard as all that, but it's important to get sort of the directions of all of this. And then from there, you can sort of put all the rest of the terms in. You end up with n equal to 2.54 newtons. And 0.3 newtons. So what you need to be able to do again is, in a relatively complex geometry, and this is a relatively complex geometry, solve through for all the terms that you need. Any questions on this? as much as possible, please redo these on your own. Go ahead. 2.54. It's a really good 4. So in anticipation of next week's lectures, I want to do this, which is the wrong way to solve these problems. But I have a kid on a swing. And thank goodness the geometry is a lot easier and it's not as much work to sort of work through. All right, kid on a swing. The kid has a mass of 27 kilos. You treat the kid as usual as a particle. And you're asked to find the tension in speed and tension in each theta equals in each, it should be in each chord. Kid starts from theta equals 90 degrees. So for an arbitrary theta, I can sort of say, well, I have 2t and I have mg. And in there, for that arbitrary theta that I'm looking at, which I should define, I have a theta. I'm treating the kid as a particle, and so the child is at some angle theta, 2t in one direction, weight acting vertically downward, but at that same instant, you have tangential and normal components of that force, the weight force, that you can sort of translate to the different directions. So if I look at the forces again, once you draw the free body diagram, you're set. It's easy. Drawing the free body diagram and doing this a lot of times really helps you get through the more complex parts. So in terms of normal components, I have a normal component pointing in towards the center. Those are the tensions in the cord. I've got the weight of the kid, which is pointing outwards. And I know that, so it's a negative value. The tangential component of the weight is acting in the tangential positive tangential direction and is positive. So I can take that tangential component, sort of put everything together, do the same thing I did in the first problem, but now for this, and integrate from v initial to v final, v dv, which equals 60. It started at 60 degrees. It ends up at 90. We'll put that in the problem later, ds. And substitute all the terms in. You end up with v equals 2.81 meters per second, and acceleration normal, which is v squared over 2 meters, which equals 2.63 meters per second squared. Any quick questions on this? Go ahead.
I know you mentioned before that for NT, like it has an origin, but with r-theta it kind of changes.
Oh, sorry. NT doesn't have an origin. NT has a path. So if you have an NT motion like a circular motion here,